Good afternoon. So, having seen that, so now we have to take care of these and design a controller appropriately. Now, let us look at performance. So, what is the first requirement of performance? The first requirement of performance is that performance can be divided into two types in control. One is called steady state performance, another is called transient performance. In general, steady state performance is much more important than transient performance, simply because of the fact that that performance holds over a much longer interval. Generally in industrial automation, the set point changes somewhat infrequently. For example, if you take a power station boiler, then its set point over a day will typically be changed 7, 8, 9 times, maybe less. So, when you will have load coming in the morning, its set point will be changed. When lighting load in the evening will start going down after, let us say 10 o'clock or 11 o'clock, load will fall, at that time you have to reduce the set point. So, there are infrequent set point changes, and in between these set points are generally maintained. This happens for a lot of process equipment. So, if you have performance degradations which are persisting during that phase when the set point is held, then that is generally considered much more serious than errors that can occur when the set point is changing or immediately after that time for a short duration. So, we would first like to ensure steady state performance, and the major consideration for that is steady state error. That is, we want that R should be equal to Y, at least in the steady state. Obviously, if R suddenly changes, Y cannot suddenly change. So, Y will have to Y will take some time to come to the level of R, but once it comes, we want that this error will be 0. We want 0 steady state error. This is our wish. So, how to obtain that, right? So, for that, so we want that this is the steady state error, that is limit of t tending. Typically, we take a unit step response. So, if the reference input suddenly changes, then how is, as time passes, does the error go to 0, that is limit of t tending to infinity E t. We can also express it in a frequency domain form, which says that, which uses the final value theorem of Laplace transforms, and which comes down to the fact that E steady state is limit of s tending to 0 1 by G s K s, right. So, so this is the steady state error, and we have to ensure, one of the prime requirements is to ensure by control that this goes to 0. So, how do we do that? So, we have to control for 0 steady state. Let us take the simplest case of proportional control. The problem of proportional control is that if you want to, proportional control is just you have a simple gain, and if you get an error of 1 volt, you generate maybe an output of 100 volts. If you get an error of 2 volts, you generate an output of 200 volts. So, just simple multiplication. Now, obviously, we want to, what do we want? We want that this R be equal to Y. So, we want to, R is a certain value. So, we want to maintain a certain value of Y. Now, naturally, it happens that for maintaining a particular value of Y, we need a particular value of U. So, for the time being, assume that this is not there. So, now how are we going to get this U? If we want to maintain this U, then we have to maintain a particular value of E. So, unless we have a certain amount of steady state error, we cannot generate U, and therefore, we cannot generate Y. So, we cannot make steady state error at 0 ever using proportional control. That is what it turns out to be. So, what happens is that there are two things that could happen. Either you could artificially increase this R, that is, if you want, let us say, an R of, really want that the output stays at 1 volt, you give an R of maybe 1.1 volt. Just what volt you have to give, that you have to calculate, but so you artificially increase 1.1 volts, so that here you get 1 volt, which is the real output you want, right. Or what you could do is, apart from what the controller is doing, you can give what is known as this manual bias, that is, you apply some additional input right directly to the plant. So, you do one of these two things. in that case you can maintain whatever output you want. But what is the problem? The main problem is that who is going to give this input? How do we know by how much? For example, if we give 1.1 volt for 1 volt, how do we know, let us say if we want an output of 3 volts, what output we have to give, by how much? So, naturally it should not require a manual manipulation, it should be done automatically, right. So, that brings us to the question that how can we automatically generate this bias input without any manual intervention. So, the question is that how to create bias input for 0 error, right. So, that is the situation described here. What should be this? So, we see that what is the device which for 0 error gives an output. So, that device is actually an integrator. So, somewhere in the loop there should be an integrator, then even if the error is 0 we will be able to give a finite output. So, there are actually 2 cases in which an integrator is required. So, the first case is this one. So, if you have an integrator here, imagine that I have written Ki by S in Laplace domain notation, which means that this is actually an integrator, that is u is equal to integral Ki E t dt. So, this is the integrator. So, this is equal to ut. So, now you see that even if after some time this at this point even if we get E goes to 0. So, for example, suppose the error goes to 0, this is y, this level is r, this is the level. So, here error is going to 0, but what will be the value of the integral, what will be the output of this block? The output of this block is going to be the area under the curve, because this is the error, this is y and this is r. So, r minus y is this vertical distance. So, this is the area, right. So, this area, even if the error remains 0, this area remains finite. So, you can generate a finite u even when the error is 0, you can keep generating it. So, having an integrator helps. There is another case in which you can have an integrator, that is the integrator is actually part of the plant itself, which means that to be able to sustain an output, the plant may not need an input all the time. So, the plant itself is an integrator. What is a typical example of this? A typical example of this is a tank. So, suppose you have a cistern, like we have in our toilets. So, you can have a flow in, and this flow in is actually, this flow is actually proportional to the level. Actually, there is a, if you might have noticed, if you have looked into the cistern, that there is a ball cock, floating ball. So, when there is no water, then the ball cock is hanging like this and water flowing. So, as water rises, so the ball cock goes up, and at a certain level the valve through which the water is flowing will actually close. So, at that level it will be maintained. So, you see now, so this tank is a plant which this tank is a plant which has an integrator with respect to flow, because the level is nothing but an integral of flow. So, at some point to be able to maintain a level, this is a level, it does not need any flow. So, the flow can go to 0. So, still, so we are having a simple proportional controller. So, the error going to 0, flow goes to 0, but still level is maintained. So, this is another situation where you can have 0 steady state error. Now, so exactly this is what happens. So, now you see, if you put the integrator, what happens is very interesting. So, what happens is that this bias input which was previously coming now comes automatically, that is the the integral output which I was talking about now increases till it can, then it goes to 0, and then if you change the set point again from here to here, again some error will be created and it will again integrate and will generate just enough output such that it can be sustained without the error. So, you see that the integrator is actually, the integrator actually works as a very interesting thing. It actually gives a bias input, but which is not manual. So, the bias input, the integrator is actually exactly like the bias input, but it generates it automatically. You do not have to give it manual, and it will adjust itself depending on the set point. So, the integrator will automatically build up and give enough additional input such that at 0 error it can be sustained. So, that is the principle by which 0 steady state error is obtained. Now, only thing is that now this has certain, there are certain drawbacks too. For example, let us see that if we give a step response, then how does it work, how does the loop work? So, you see that suppose the process starts from here, okay. So, the process starts from here and starts, so as you have given, so here there is a lot of error. So, the proportional controller now generates a positive input which drives the plant. So, the plant goes up and typical we are likely to get a step response like this. So, what happens during this phase? During this phase you have proportional is positive, error is positive, so output is positive, but since the error is decreasing, so the output is going down. So, it is positive, but going down, that is the output of the proportional controller. What does the integral controller do? The integral controller is also positive because it is integrating positive error, and it is increasing because the area, as it is going with time, this area is continuously increasing. So, it is positive and going up, increasing, right. So, what happens at this point? At this point error is 0. So, the proportional controller output is 0, but because the integral controller output is still positive, so the plant continues on this journey in this path, right. Now, when it is here, let us say when it is here, the proportional controller around this point P is negative, but I is still positive because of the fact that there is already a large positive integral accumulated here. So, here integral is negative, this part of the integral is negative, but still there is a large positive integral. So, the overall net output is maybe still positive. So, it continues on this journey, but eventually this integral value also reduces and the proportional controller value also becomes enough negative. So, the overall input turns negative and the plant turns to move. Now, again the same thing happens here. Once it crosses this line, now again it will oscillate. So, you see that typically because of integral control there tends to be an oscillation. So, there tends to be a high overshoot and an oscillation. So, this is a drawback of integral control, that is, to gain steady state error, to gain 0 steady state error, this is the price that you are paying, that in your transient response you are likely to get some overshoot. So, that is the picture for the step response. So, we want to improve transient response without sacrificing the steady state error. So, if we want to do that, then what we have to do is that around this point only here we have to keep braking, we have to keep braking and around this point so that we can quickly turn. So, what happens is that here now we have to slow down. So, slowing down means during this phase we have to create more negative input which will grow towards this point. As it comes closer, it should this negative input should increase. Similarly, around this point this negative input should also keep increasing, so that it quickly turns and then actually it will settle very fast. So, you see it will not oscillate. If we want that it does not oscillate so many times, but rather follows this yellow curve, maybe does a small overshoot and then immediately settles down. This is the kind of curve that we want. So, now it turns out that this kind of curve we can obtain if we add a derivative term to error, right. So, we want to reduce rise time. What is rise time? We want to reduce rise time is we want to reduce this time. We want to, typically speaking, we want to reduce overshoot, that is this height, and we want to also reduce settling time, that is total time taken for it to come to a steady state. So, we want to reduce that all these. Now, getting all this is somewhat difficult, and that is why you need to have a non-trivial tuning exercise to come to a compromise between these, because typically what we do is, it turns out that these things can be achieved. We have already discussed proportional and integral controller, and we have also seen that adding a derivative will try to break so that it does not go towards much overshoot. So, we need a proportional controller, because if you do not have a proportional controller, then there will tend to be too much of oscillation. We need an integral controller to have 0 steady state error, and we need to have a derivative controller to have low overshoot and fast settling time, and we need to tune these gains Kp, Ki and Kd nicely, so that we get a good transient response without sacrificing on the 0 steady state error. One thing interesting to see is that this, so we now calculate input like this. Now, interestingly, that you see that in the steady state the total E is 0. So, therefore, this term is 0. So, the proportional controller is 0, and since E is not also changing, so there is a d dt is also 0. So, that is also gone. So, we only have the whole output coming from the integral part. So, the 0 steady state error concept that we have studied for the integral control holds. Now, so as I said that we need we are looking for a step response like this. This would be a very good step response, and we, if we can make it even sharper, even better, but generally if we want to make it sharper, then if we can make it like this, even better. So, this is a good step response that we would like to achieve. So, now come to the point of disturbance rejection. So, what is the disturbance response? The disturbance, so let us talk about, there are several types of disturbances, and you can do the same kind of analysis, but the most predominant disturbance which occurs generally is the load disturbance in a process, occur due to various reasons, property variations of materials, variations in power sources, voltages, variations in pressure sources, all sorts of things. So, it turns out that the transfer function, we want to reduce the effect of d0 on y. So, what is the transfer function between y and d0? That turns out to be this. So, now again we see that if we have, so it is not possible to exactly neutralize all kinds of disturbances, but let us say one of the major kinds of disturbances is step disturbance again, that is disturbances which change once or twice and then stay on. Okay. So, if you have step disturbances, then you can again see that that if you have if you have an integral, then this term will actually go very high as s tends to 0. So, the effect of, so but for the same reason exactly similar transfer function is coming. So, the same reason why E goes to 0 with integral control, if you put integral control, even the effect of step disturbances will also go away, because the integral value will rise and it will provide the additional torque to actually take care of the disturbance. So, it will produce the integral will rise and it will here it will, instead of producing y, it will automatically produce an output y plus d0 or rather y minus d0. So, that after plus d0 you will get the desired value of y. So, this is going to happen. So, integral control is one of the major ways of reducing disturbance response. So, this is now let us look at some other issues. For example, we have to actually remember these things, because they are very practical issues and we possibly did not learn about these in our earlier controls course, where we treated things rather ideally, but we must remember here that some other non-idealnesses exist. For example, there can be very often there can be actuator saturation, that is the characteristic of this is the control input Ci and this is the plant input Pi. So, this is the actuator characteristic. So, as you increase the control input, the actuator will also proportionally include the plant input, but only up to a certain point, after which it will saturate. So, if you give more and more control input, it will not give you proportionally high plant input. So, the actuators typically will saturate. Now, when the actuator saturates, effectively the feedback loop is opened, because the effect of the error no longer transmits to the output or rather the plant input. So, the input does not change in response to the error, but is held constant. That is the case of an open loop operation. So, your control is gone, and not only that, sometimes as we shall see later that persistent actuator saturation has very bad effects on controllers, especially because of the fact that controllers have memory. So, this is a particular phenomenon which occurs in PID controllers, and we are going to take a look at it in great detail in the next lecture. So, next issue that we should look at is sensor bias. So, remember that if you have a sensor bias, sensor has errors, then sensors are the eyes of the controller. So, whatever the sensor sees, that the controller simply works on that. So, if you have bias, you will think that is the controller will produce an input which will have 0 error, but actually there will be non-zero error. So, that's so you have 0 error, but you have non-zero error. Similarly, we have to remember that you always have, actually you design controllers based on some models, but it always turns out that these models are actually inaccurate. So, you are always going to have model errors, and these model errors are typically dominant in the high frequency band. And now remember that if you have inaccuracy in the high frequency band, it is the errors in the high, actually typically instability occurs in the high frequency band, not in the DC band, lower frequency band. So, if you have modeling error in the high frequency band, then such modeling inaccuracies can also lead to stability problems. So, we have to remember these things. So, to take care of these things, various kinds of other architectures are possible than what we have, that is the loop structure, what feedback we will use, how we will use the controllers, and we will see some of them, for example, feed forward configuration, cascade configuration, we will see all of them. So, they are possible. Finally, while we are moving towards the conclusion, let me mention some of my pet facts about control in colloquial terms. So, I say that what you feedback is what you control. So the controller exactly tries to maintain the feedback. So, if your feedback is erroneous, then your control is erroneous. If you are sitting in the middle of the room, and if you are put your temperature sensor at the roof of the room, then you are controlling the temperature at the roof of the room, not in the middle of the room, right. Then when you what you cannot actuate, you cannot control. So, you may be giving whatever in output from the controller, you may be using a fancy algorithm, but if you cannot actuate it, then you are not controlling it. If you can measure or estimate the disturbances, then you can compensate them. So, one of I mean there are many advanced algorithms which precisely try to do that. Stability is basically stability is not enough. Stability is barely basic performance. You must ensure stability and then ensure performance. But while you ensure performance, if you as you try to go more and more, drive more and more and improve performance, eventually instability results. So, instability is actually generally decides the maximum performance that you can achieve, and models are always approximate. Most systems are actually nonlinear, but that does not mean that we can work with approximate. So, linear control can work very well for nonlinear plans, but sometimes nonlinear control may be working better, but 95% of industrial controllers are linear. So, we have come to the end of the lesson, and let us review quickly. So, we looked at the objectives of automatic control: maintain stability, follow set point, reject disturbance. We looked at stability and found the causes of stability in causes of instability in a process loop. We looked at steady state error and the ways of reducing it, and we also looked at the ways of reducing transient performance, keeping the steady state error at 0. So, we saw that the PID control is a very effective way of and simple and effective way of doing that, and eventually we saw that PID control can also do some amount of very common disturbance rejections. So, that is the end of the lesson. Here are some points for you to ponder. First is that state the 3 major objectives of automatic control, which I have just now said. State 3 major causes of instability in a control loop, and give, this is tricky, try it, give an example for each case, practical example. And is it possible for a proportional controller to achieve 0 steady state error? I have already explained an example. You try to explain it in your own language, and explain how a PID controller can achieve good transient performance as well as 0 steady state response. And finally, justify or contradict the statement that PID control achieves 0 steady state error with step set points and disturbances. Thank you very much. We will see the next lecture.